Okay, so here I have a problem that's written implicitly, and I'm asking you for vertical and horizontal tangent. We talked about horizontal tangent lines, right? Now we gotta talk about vertical tangent lines. So at least write down the problem. I see the word tangent line. We know we need a derivative. Okay. The derivative of 4x squared is 8x plus y squared 2y dy dx minus 8 plus 4 dy dx plus equals 0. Awesome. So are you okay if we leave dy dx on the left side, move things over to the right side that don't have it? So 2y dy dx plus 4 dy dx. I'm going to write 8 minus 8x. Is that okay? Does it matter the order in which you write those? Nope, it sure doesn't. Okay. Sorry, I'm just going to get my notes here. We can factor out dy dx. And then divide that over. So dy dx is 8 minus 8x over 2y plus 4. Like I said, if you want to simplify that a little bit, you are more than welcome to, but it is not necessary. All right. Let's go with the one we know how to do. Okay? We know how to find horizontal tangent lines. Horizontal tangent lines mean that our slope is what? 0. Our slope is 0. Okay? So here is my slope. I want dy dx to equal 0. Now, if we have a fraction that equals 0, what do we really care about equaling 0? The numerator. Okay? Because if we set this entire fraction equal to 0, we take that denominator and multiply it over, and then it's still just the numerator equals 0 anyway. So I'm just going to save myself some pencil lead, okay, or marker in this case. So this occurs when x is 1. Well, what's y? Okay, we need to plug it into the original equation so we know what y is. Not a problem, right? 4x squared plus y squared minus 8x plus 4y plus 4 equals 0. You guys have all taken years of algebra. It's not scary. Especially because what happens? This is 4 minus 8 plus 4. y squared plus 4y equals 0. So when x is 1 and we plug it in, we get y to be 0 and negative 4. So this is happening at two different places. Okay? We have the coordinate 1, 0 and 1, negative 4. Okay? Well, why do we have this happening at two different places? If you recall back to April of last semester, if we had an equation where x was squared, y was squared, they were both positive, but they had different coefficients, we have an ellipse. Does it make sense that there are two places on an ellipse that have horizontal tangent lines? For sure. How many places will we find that have vertical tangent lines? 2. So let's talk about those. Questions on this before we get to vertical? Yes.
Do you have to write it into the equation or no? Just leave it as a point?
So in this case, in this example, I asked for the coordinates,
Okay.
and so just the coordinates are fine. Okay. All right. For vertical, what does that mean about slope? The slope is undefined. Okay, a vertical line has undefined slope. So if we want a vertical tangent line, what do we want to have happen with our derivative? We want it to be undefined, which means if we have a fraction, we want that denominator to be 0. Okay, so we're going to take 2y plus 4 and set it equal to 0. Which means y is negative 2. Okay. Usually the calculus part isn't so bad. It's like taking that and plugging it back in. That takes a little bit more work. Okay. Not difficult work, just kind of some tedious calculations. Okay. So now that we know what happens when y is negative 2, let's go back and figure out what our x value, or values, we're going to find two places. Let's figure out what those would be. So we have 4x squared plus y squared minus 8x plus 4y plus 4 equals 0. I'm taking that y value and plugging it back in. We have some nice things happening. What happens again? Okay. We're left with 4x squared minus 8x equals 0, aren't we? That is really nice, because that's like the easiest factoring we could ask for, right? We have a GCF. So we found two different places where y is negative 2. So we have a vertical tangent at 0, negative 2, and we have a vertical tangent at 2, negative 2. I will tell you that this concept of horizontal and vertical tangent lines is a big topic they like to grab for a free response problem. So we're actually going to get to look at a free response problem today. Okay. Any questions before we look at a second derivative? Okay. Second thing I want to look at is taking an implicit function and finding the second derivative. So write down this implicit function, please. Okay, so first let's find dy dx. You ready? Derivative of y squared. 2y dy dx equals derivative of x squared plus 2x. 2x plus 2. Okay. So when we find dy dx, we have 2x plus 2, and then we would divide that 2y over. Now, normally I'd say, you know what, just leave it the way that it is. But since we have to take this and find the second derivative, I'm going to go ahead and simplify, because when we find another derivative, simplifying makes our lives a little bit easier. So let's go ahead and write dy dx as x plus 1 over y. Is that okay? We do that? Okay. If you don't, it is perfectly fine. It's just going to add a lot more coefficients inside of your next derivative. Okay. All right, so now we're taking the second derivative, and our process doesn't change. It's just an implicit derivative. Okay, so what do we have for dy dx? We have a quotient. So when we go to take the second derivative, when we go to take the second derivative, we're going to do the quotient rule. Okay, so derivative of the numerator times the denominator minus the numerator times, what's the derivative of the denominator? Dy dx. All over denominator squared. Okay. Now, we don't need to solve for anything. We are already solved for the second derivative. However, do we know what dy dx is? We know what dy dx is. We know that dy dx is x plus 1 over y. More than likely, I'm going to ask you to evaluate that equipment. Okay, more than likely. But now we have our second derivative. Yes. Okay. You don't have to rewrite this. Okay, this is perfectly fine the way that it is. We are not done for the day. Did you hear me say that this is a popular topic for a free response question? All right. Here is a free response question. Consider the curve, blah, 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 blah. Show that the derivative is this. Hey, I'm giving you the answer. Just do the work to show that that's true. B, find all the points whose x-coordinate is 1 and write an equation for the tangent line at each of these points. And C, find the x-coordinate of each point on the curve where the tangent line is vertical. I'm going to give you about 15 minutes to see what you can do, and then I'll go through the answers. Okay, you can work together. No calculator, you may begin.